Okay, guys, are you ready to go, huh? Well, you're all very welcome. This is Mathematics 254, so if you're on the wrong bus, now would be the time to find the right one. My name's Newell, and I am the instructor here in this course. And I'd like to introduce you to your TAs who came along today. We have Jun Wang. Jun, stand up. Lanbo Fang. And Wan Tao. Where's Wan? Over there. And you will all be meeting these characters tomorrow. And I think you will enjoy them very much. Okay? Now, come in. Don't be shy. Well, maybe they just don't want. I want to just emphasize a couple of things at the very beginning. First of all the notes for this course are going to be on your D2L site. Now, we had a little trouble. The D2L site was working very well, and it's still working very well, but the address that I give you in the syllabus for downloading the software is, let us say, less than reliable. Okay, it was working fine a few days ago, but this is an alternative address, so I'd like you to copy that down, okay? And this will be important that you download the software. We're only going to use 2 pieces of it, but it'll be very useful and very important for the class. So download this address. If you have any troubles, bring your little computer along to your recitation class, and the TAs will have on their memory sticks the program so that you can download it during your recitation class tomorrow. Mainly you can get by with the notes I have on D2L. Currently, there's the introduction, the syllabus, and both of these are available. I actually copied them off so you guys can get copies at the end of the class. And then lectures 1 and 2 and lectures 3 and 4 are up on D2L. I'm updating the other ones. I might put the old ones on there because the updates aren't going to change things very much, so that those of you who might like to get an idea of the full terms worth, the full menu, can look at those. But certainly within the next month or so, the full course will be up. But for now, you'll be at least a week or 2 ahead of time in the notes. Now, some of you do like to use books, and that's fine. And this book, this is recommended, the Saf and Snyder book is fine. And in fact, when I put set homework, a lot of the set homework, SHW is set homework, it refers to the textbook. What I would suggest is that you might, first of all, it's a good idea to work in groups, doing homework and in fact trying to understand the material. And maybe between the 4 or 5 working in a group, you could have 1 textbook. That'll save you quite a bit of money. Textbooks are inordinately expensive these days. Has anybody bought a textbook for this class? You did. How much did you pay for that?
It's like 120, 140 something.
Yeah. So it's grand to have the book. I mean, it'll serve you in good stead, but the notes will be sufficient for all the material you're going to cover. Seat for you here.
Does anyone sitting there?
Now, all of you who were too shy to come in and who have just entered the room, I want you to talk to neighbors, not during class, but after class. Talk to your neighbor about what I have just told them, in particular in connection with the correct address to download the software. And also the admonition that you turn up at your recitations. It's very important. You'll be getting material in your recitations tomorrow. For instance, homework number 1 will be given out then, so be there. All right. The other thing I want to say before we start into the good stuff is it's a big class. You know, think of when you go to the movies, there's nothing more infuriating as when the good movie starts to have some guy coming in with a pile of popcorn and pushing his way along the row. It's very annoying. So, if by happen chance you are late on any one day, and there's always reasons that people on one instance or another are late, come in that door, not this door, and come in quietly, okay? But I want to ask most of you, in fact all of you, but the occasional latecomer, I want all of you to try and turn up on time. That way we can finish on time, and that way not everybody is interrupted when you come in. Is that okay? Is that understood? Can you hear me at the back clearly, or do you want me to put on the microphone? Hands up if you do not hear me clearly. Good. No hands up. Good. I don't have to wear that microphone. The microphone I am wearing actually is a direct feed into the videoing equipment. Now, it's not that you're going to be on television tonight. I'm sorry, but we're actually videoing the course so that it would be available to you in addition to the notes online. We hope sometime during this term, or maybe at the end of term, to get the full set of lectures up on a video, so that if you miss certain parts of the lectures or there's certain material you didn't quite understand when you were when you're studying it later, you can go back and watch on the video. So I hope you will forgive us if I don't think there's too much disruption. Camelia and Ed are doing the videoing, and I think they'll be rather unobtrusive. If you have a particular objection to them panning around occasionally and having you in focus, let me know, and we will we'll edit you out of any pictures that turn up. But for the most part, the camera will be on me and the whiteboards. Most of the course I will try and lay out for you on the whiteboards. Occasionally we will be using, when I'm showing you examples of how to use the software, we'll be using the computer and the software program with the projector. And then, of course, we pull the screens down. But for most of the time, we'll work on the whiteboard. So I want you to tell me if it should be that I write too small or I don't write clearly. Okay? Now, why do we study differential equations? What's interesting? Yes, question. You're answering the question before I had it half out. If you'd had a buzzer, you'd have pressed it, right? Well done. Yes, that's true. Differential equation, in fact, all of mathematics. They say mathematics is the queen of the sciences. A lot of the mathematics you see early on in life tends to be very kind of formulaic, and you're calculating algebraic formulas and that sort of thing. And perhaps you do not see the connections with all the ologies. I mean, how many ologies are there? There's geology, immunology. Well, I think mathematics may not have too much to say about Scientology or maybe even theology in general. But for most of the ologies, mathematics is key. For instance, how many people here are pursuing the biological sciences? Okay? Now, have you learned a little bit about genetics? Right? Do you know who Mendel is? Right. All of Mendel's work, brilliant pioneering work, done many years before Darwin came along even, relies on what subjects? You work out what the chances of various, you work out the number of ways in which various combinations can occur of recessive and dominant genes, for example. It's all combinatorics and probability. Okay? Differential equations also. It has, in fact, a very special role in the physical sciences because it explains or it tries to describe and capture how things move, change, and evolve. Okay? For instance, the motion of the Earth around the Sun is captured by a differential equation. Okay? The motion of the atmosphere on the Earth and all the planets are captured by differential equations. The interaction between species, say foxes and rabbits, we'll be doing this example later in class. The interaction between species, they are described by differential equations. The propagation of information along nerve axons are described by differential equations. In fact, the differential equations, they're very simple. In fact, in many cases, the differential equations that describe all these wonderful things, you will meet this term and you will learn how to handle. But Hodgkin and Huxley got the Nobel Prize for describing the propagation of pulses along nerves. Hodgkin actually is not the Dorothy Hodgkin who died recently. She also got the Nobel Prize. She was one of the first women to do so. She was a crystallographer. Willard Libby got the Nobel Prize for something you're going to see within 2 weeks of this class. He used a very simple differential equation to essentially figure out a method of dating rocks, okay? Dating lots of things, using a certain principle that the rate of decay of any radioactive substance is proportional to the amount of the substance present at any time. Circuits, electrical circuits. How many people here are electrical engineers? Or yes? Only one. Two. Oh, sorry. Where are you? Okay. 3, 4. Good. All right. You are now. Have you done a circuits course yet?
I'm taking one.
You're taking one. Well, you tell me if I teach it better than the other guy. Okay? All right. But we're going to be working on circuits. What are differential equations? They're simply relations between some variable, like, say, the temperature in the atmosphere, okay, the temperature in this room, and certain variables we call independent variables, like time or space. Like the temperature of this room, if we took a reading of it over the course of a day or two, would change up and down. Okay? At night it would be lower, in the day it would be higher. It depends on the efficiency of the air conditioning, of course, but whatever. You can see these variables change in time, and the way they're changed in time are captured by certain basic principles, which come from ideas in physics and chemistry, but which are written down, they're mathematized in the form of differential equations. So a very important ingredient in this course, I'm not just going to tell you how to solve equations. If you think you're just coming here to learn exercises on solving equations of this stripe and that stripe, let me disabuse you of that notion right now. Learning about differential equations, we're going to learn, first of all, that to formulate the problem as a differential equation. Then we will learn how to solve certain classes, categories. And finally, we'll turn to interpreting the solution. Does what the solution says make sense? What does it suggest we might do to expand the questions we're asking? These sort of questions are very important. So, formulation. Now, formulation is something most of you, when you go out to work or when you're faced with a problem that can be mathematized, it's very rarely going to be given to you. Your boss isn't going to come along and say, hey Fred, here's the differential equation, would you come up with the solution? No, he'll say, look, we have this problem, okay? We're looking at the stability of the rubber composition in this tire when it's subjected to various friction forces. Now, the behavior, we measure certain things and it seems to be like this. Can you kind of come up with a model that we might be able to kind of simulate what's actually going on? That's what he'll say to you. And then you're left there and you can flick through all those textbooks you like and you're not going to find exactly how to formulate that problem. So it's very useful in your first course to learn about formulating problems as differential equations, because the more examples you do, the better you get at this particular art. So that's what I'm going to start off first. I'm going to just start off with 3 examples. The first example is the following. I'm going to ask you the following. Here's a plane. Okay? I'm going to draw a curve in the plane. Okay? I'm only going to draw a bit of it, but say here. And I'm going to ask, hello? Can you find a seat, please? Good man. I'm going to ask, what curves in the plane have the property that at every point their tangent is perpendicular to the line joining that point to the origin? Okay? Now that's a sensible question. Okay? So I want to know what curves y equals f of x has the property that the angle, take any point on that curve, xy, this is a point xy, okay, that the tangent to the curve here is perpendicular to the line joining that point to the origin. Now, how do we mathematize that? Well, one thing we could do, excuse me a sec. One thing, well, let's write down in terms of mathematical quantities, what is tangent of phi in terms of x and y? What's the tangent of phi in terms of x and y? Yes? Y over x. Okay. What's the tangent of psi? Now you're going to get into differentials, aren't you? What's tan psi? In your calculus, you learned the derivative of a curve f prime. dy by dx. What's the tangent of this angle? If this curve is y equals f of x, what's the tangent?
Is it negative x over y?
It's what?
Negative x over y?
Negative x over y? No. No, it's dy by dx, isn't it? dy by dx, right? At the point xy. In other words, f prime, dy by dx would be df by dx, f prime, right? Didn't you learn that in calculus? Where did you learn your calculus? Yes, yes, you. U of A. And did you know that?
Yeah.
Good, but you didn't want to tell me. Right. All right. Now, what have I said? I said I want to situations where psi minus phi is pi by 2, 90 degrees. Right? That means these are perpendicular because this plus this is 180 degrees or pi, and this plus this is pi. So the difference between that and that is pi by 2. Okay? So now your trigonometry. Tan of psi minus phi equals, what is tan of psi minus phi? In terms of tan of psi and tan of phi. Where did you do your trigonometry? All right. Well, work it out then. Work it out. Actually, the way I'd work it out if I didn't remember the formula is I'd say it's sine of psi minus phi or cosine. And I'd remember the formula for the sine and the cosine. But I'll tell you what the answer is. It's tan psi minus tan phi divided by 1 plus tan phi tan psi. Okay, that's what it is. Okay? Now, if psi minus phi is pi by 2, what's the tangent of pi by 2? Okay, remember what tangent is. I'll draw a little curve here. Okay, do it up here. What's the tan of that angle? It's this guy over this guy, right? Now, if this goes up to pi by 2, the denominator is getting very small. 0. So tan of 90, or tan of pi by 2 is infinity. Infinity. Okay? So, how do I make this expression infinity? I have to take this guy to be 0. Right? If I take the bottom to be 0, then tan of psi minus phi is something over 0, which is infinity. Okay? So, let's write this down in terms of these expressions. So, it's 1 plus y over x times dy by dx equals 0. Right? That's 1 plus tan phi tan psi equals 0. I'll write this as dy by dx equals minus x over y. So that's our differential equation. It relates the change in y with respect to x in terms of x and y, some function of x and y. Okay? So, if we can find a function y of x which satisfies this relation, this expression, we will have found a curve which has the required property. In fact, we're going to find lots of such curves. And either a little later today or beginning tomorrow, we'll actually figure out what curves they are. Right? So that wasn't so hard. Now, I'd like some guy or gal, who considers themselves who likes challenges. Supposing I told you, find the curve or set of curves where the tangent at any point makes an angle of 45 or pi by 4 with the line joined to the origin. Okay? Could you try and write down for me for Thursday the differential equation which would express that fact? That's actually also something you'll be able to solve at the end of the course. So you're going to find out what that... Can anybody guess the answer, by the way? Yes. Who said that? Say it out loud.
Circle.
Circle. Any circle or one circle?
Circle centered about the origin.
Circle centered, any circle centered by at the origin. So there's a whole family of possible solutions. Okay? And you sort of know that from your geometry, like if you have circles. So we will hope that the solutions here, when we solve the equations, give us circles. Okay? All right. Problem number 2, or example number 2. You're walking along the road and you find a dead body. So there he is, little guy. Now, he's obviously dead, but still a little warm. But he's rapidly cooling because the air is colder. So out here is colder, like this. Okay. I'd like to establish the time of death. I happen to have a thermometer on me. So I take his temperature when I find him. And then I take his temperature again an hour later, say. Okay? And from that, and from a knowledge of how a body cools, we will be able to determine the time of death. Yes?
Would it be a little more straightforward, just taking its temperature and the outside temperature, and then just use those two temperatures at one time to calculate the time of death?
Yes, but that's you walking along the road. I'm telling you what I did. All right. I'm going to have you sit up in the front row in future here. Good man. Well, now, so how does a body cool? First of all, how do we describe the temperature of the body, okay? It's going to change as a function of time. So we'll measure it in Fahrenheit, say, T of T. That's the temperature of the body in degrees Fahrenheit. Degrees Fahrenheit. And we're going to measure T in hours. Okay? Now, roughly, what do you think dt by dt, the rate of change of temperature with time, it measures the heat loss from the body. How does heat move? How does heat move from body? What are the mechanisms by which heat is transferred? Yes?
particles of the air moving at a certain speed, collide with particles of the body that have a certain temperature, and then those particles of air take away some of that energy.
That's right. So this is molecular particles. It's just a little. That's called conduction. Okay, conduction. That essentially you conduct away heat. Actually, you don't. Conduction isn't very efficient, because if I stood next to you and I was very hot, I'd have to stand very close to you before you'd feel my heat. Okay, you'd notice it because I'd be sweating before you'd actually feel it. So actually, conduction is not really a very effective way. Any other mechanism? Yes. Radiation, yes, that's probably the largest influence in this situation. A body, a black body, a body radiates heat or energy proportional to the 4th power of its temperature. Except, of course, then you have to remember that you're measuring temperature in degrees Kelvin. Okay? Absolute. Like we measure degrees, we like to use the unit centigrade because it's boiling and freezing point of water, 0 to 100. Fahrenheit, 32 to 212, is the same range, but Kelvin is centigrade, except its 0 point is negative 273 on the centigrade range. Okay. So the body would have a certain temperature. He'd be radiating proportional to the 4th power of his temperature. But he'd also be receiving heat, wouldn't he? By radiation from the atmosphere. So he would be radiating at proportional to T to the 4, and he'd be receiving heat proportional to, we'll say, T air. We'll call the air temperature T air. Okay. So what would be going out would be proportional to T to the 4. What would be coming in proportional to T air to the 4. But actually, because these temperatures, when measured in degrees Kelvin, are quite close to each other, we're talking about the difference between what's a body temperature in, I know it in Fahrenheit, 98.
98.6?
Yeah, but what's it in centigrade? It's about 37. Yeah. And so the difference between that and the air temperature is only a couple of degrees. So actually the 4th power, the difference in the 4th power, you can approximate by essentially you do a Taylor series. You've heard of Taylor series. And you can write it as just the difference in the temperatures times a constant. Okay? And that becomes known as Newton's law of cooling. Yes, it's the same Newton. So T of T minus T of air. But it's completely consistent with the law of radiation. Most of your caloric loss each day, okay, that you've taken in, how many calories do you take in every day? 2,500, right? And you lose 2,500 because you're maintaining your weight. So most of that is radiation. Not all of it. Some of it is convection. That's the third means by which heat is transferred. And that's a little bit like the conduction, except now it's the large motion of the air coming by your body, just gets close to your body, takes away the heat. Okay? Anyway, so this is the equation. Now, can anybody tell me, what do you think the sign, S-I-G-N, of C should be? Right, very good. It has to be negative, because otherwise the body would be getting hotter. If the air was colder than the body, we expect, on average, the heat will flow out to the air. So you're quite right. So we write this down as minus K, minus a constant times this. Now, at the beginning, we might be given the basic temperature, T of 0. So when the man died, what would his temperature be? Let's imagine he was he was mugged, so he was healthy before he got mugged. What's his temperature? 98.4. We're measuring in degrees Fahrenheit. Okay. Now, I thought it was 98.6. Is it 4 or 6? Yeah. Now, we located him at a time after he died. We don't know. This is the time of discovery. TD is the time of discovery. Discovery time. Okay? And that's, say I stick the thermometer in and I get 88.6. And an hour later, I find it's 78.6. And I'll say the T of the air all the time was 68.6 to make the calculation nice and easy. Okay, but you see, this is a differential equation. It relates the change in the variable T, capital T standing for temperature, to the instantaneous value of the temperature and other quantities. Now, if the air temperature, if you knew it changed and how it changed in a certain way, you could put in how that changes as a given function of the independent variable T. Okay, so this is an equation, for instance, that we're going to be solving as well in the next, in fact, few weeks. Third problem. Third example. This is very important for people who are mixing up solutions. And it's good for any solute-solvent situation. But I'm going to think in terms of brine, salt dissolved in water. Okay? So we'll talk about it in that context. So here's the situation. I have a valve and a pipe. There's the valve A. And here's a big pot, mixing pot. And below it then I have another pipe and another valve B, and the output goes into a container here. Okay? Now, I start off with G gallons of fluid in the tank. Okay? And the concentration initially, C0 is the initial concentration. I'm going to measure the amount. We're going to measure the amount of salt in the tank by the variable x of t. Okay, I'm going to measure t in minutes. Okay. I'm going to measure volume in gallons. And the concentration, say the total volume in here is V. The concentration, if there's xt pounds of salt in V gallons, the concentration would be x over V, right? So the concentration would be x over V. And what would the units of this be? This is pounds, okay? And volume we measure in gallons. So this would be pounds per gallon. Pounds per gallon. Now, I have when I open this valve, a brine solution with flow rate Q1, say, gallons per minute, flows in, and each gallon, okay, the concentration of salt initially, or in this input thing, is C1, and it's in pounds per gallon. Okay? So you're flowing new brine in at the rate of so many gallons, Q1 gallons per minute. Each gallon that comes in contains C1 pounds of salt. If B is open, his output rate is Q2 gallons per minute. Okay? And his concentration would be, of course, whatever is the concentration of the mixed solution. In here, I have a good stick, and I keep this well stirred so that the salt is homogeneously distributed throughout the tank. Now, first question. What is the volume at time t? What's the volume in the tank at time t? What's the initial volume? G, right? And how many gallons are flowing in per minute? Q1. So in a time t, how many gallons have gone in? Q1t. How many gallons are flowing out? Q2. And after time t minutes, how many have Q2t? So it'll be G plus Q1 minus Q2t. Okay? So the concentration at time t, t minutes, is, as you told me, x of t divided by the volume, which is G plus Q1 minus Q2t. Great. Now, so I want to do the following problem. Now, x of naught, the number of pounds initially in the tank. Can anybody tell me how many pounds initially are in the tank? How many gallons were in the tank initially? G. Each gallon contained C naught pounds, so it would be G times C naught. Okay? Okay, so we're going to start off with a situation where we have G times C naught pounds of salt in the tank initially. Then I'm opening the valves A and B simultaneously. The new brine is flushing in. The mixed solution is flushing out. And I would like to determine how many pounds, or what's the concentration in the tank after t minutes. Okay? So, I want to write down an expression which tells me about the rate of change of the number of pounds of salt in the tank at time t. So, in an interval of time t to t plus delta t, okay, so the amount in, the rate at which things come in, dx by dt. Okay? That's the rate of change of x. What is the units of this? What are the units of dx by dt?
Pounds per minute.
Pounds per minute. Very good. Pounds per minute. Pounds per minute. All right. So we figure how many pounds come in per minute and how many pounds go out per minute. So how many pounds of salt come in every minute? Yes, can whoever said that speak up a little louder? Q1 times C1. You see? Because it's Q1 gallons per minute, okay, times C1 pounds per gallon. When I multiply those together, what is the units of this product, Q1, C1? Pounds, right. The gallons cross out, and we get pounds per minute. That's what we like. So this is Q1, C1. Now, what is the amount that flows out per minute? What's the rate of flowing out? Q2 is correct. Now, what's the concentration? What's the instantaneous concentration in the tank? It's what? It's, no, it's, the concentration at time t is x of t divided the volume at t. So it's x of t times g plus q1 minus q2 times t. And what's the initial condition? The initial state is here. This is how x changes. So if I can solve that differential equation, this is a differential equation because it relates the change of the variable x with respect to time to the instantaneous value of x and time and given time dependencies. Okay, let's take an example just. Supposing I took Q1 and Q2 are both 2 gallons per minute. C1 is 1 pound per gallon. C0 is half a pound per gallon. Okay? Then notice that the volume never changes because the inflow rate and the outflow rate are the same. So then the equation would be dx by dt would be Q1 times C1, that's 2, minus Q2 is 2, x divided by g, because this is 0, because Q1 is Q2, x over 10, 2 over 10 is 1 over 5, so it would be 1 over 5 times x. And the initial condition, x of 0, would be 5. So this is a relation that tells us how the rate of change of this variable x depends on x and other things. Okay? So if we can solve this, we can figure out what the concentration of the outflow, or of the tank at time, of the brine in the tank at time t is. Okay? I want you throughout all this term to get your units correct. Okay? An equation is not saying two numbers are equal, but it says two things are the same. So 11 apples is not the same as 11 oranges, even though the 11s are the same. Okay? I'm reminded of this. I spend the summers in Ireland. Lovely place up in Donegal on the northwest coast. And it's a small town, but we're very lucky because it's a very beautiful area. But we also have, there's a little swimming pool in the town, you know, an indoor one, because swimming in the sea, you can probably swim comfortably in the sea for like more than 2 or 3 minutes. maybe for 2 days in August or something like that. I mean, the sea is cool, so it's grand to have the old swimming pool. So there's a few of us who go up in the mornings and swim. And actually, it's myself and 4 ladies. And the 4 ladies, the senior lady, she's in her 80s. Wonderful lady. Grania is her name. Now, Grania was caught the other day flying over Fannet Bridge. There's this lovely bridge. This is a real example of pork. Pork happens in Ireland and Irish politics as well as the US politics. They built this bridge between 2 peninsulas, and the traffic over it would be about 10 people per day, you know. Grania is one of these coming over. She'd have to go all the way around a big inlet if she didn't have the bridge. But she was flying over the bridge one day, and she was stopped by the local guard as she had gone. And the guard says, Grania, says, you were speeding. I wasn't. She says, I wasn't even doing 80, she says. And the guard says to her, well, look, Grania, now, the signs in Ireland are in kilometres per hour, not miles per hour. So you see, it matters what the units are. Right. Anyway, I don't think Grania got fined, but anyway. For instance, you've seen that cartoon of this, you know, you see this guy, he's got Einstein look about him, hair splayed all over the place, and he's at the blackboard and he's written down E equals mc cubed. Doesn't like that, he crosses that out, and then he mc to the 5th, and no, he doesn't like that, and eventually comes to mc squared, okay? But really, that's a nonsense cartoon, because you guys, after my preaching to you for a term, will know that the units have to balance on both sides. And the only combination of mass and speed of light, the only combination which gives you the units of energy, which is like force by distance, are m L divided by t squared, mass times acceleration, times distance L, so ml squared over t squared. The only combination would be mc squared. Now, the constant in front, that's a different question. But you know automatically that the energy, if it's the energy of something, whatever it is, only depends on mass and the speed of light, it's got to be mc squared. Now, whether it's 45 mc squared or 1 mc squared or whatever, this is, of course, where a lot of the discussion comes in. But we're going to learn how to use this idea. A pendulum, okay? You know what a pendulum is, like a grandfather clock. I mean, in this digital age, I guess none of you have ever seen a clock. I mean, we used to have clocks that go tick, tock, all night, tick, tock. And you probably learned the formula for the period of the pendulum in school, did you? Do you remember what it was? Yeah, 2 pi. No. Because L over G would have units L. G is units of acceleration, so that would be L over T squared. So that would have units of time squared. So what is it now? What's it got to be? Can't be L over G squared, because that is units of seconds squared. How do I get to seconds from seconds squared? I take the square root. So what's the formula now? What's the formula for the period of the pendulum? 2 pi square root L over G. Now, supposing the pendulum, though, is swinging like this. What do you think the L and G dependence is? It actually has to be the same. The only thing that changes is the 2 pi. The 2 pi, when you have very small oscillations, which case we'll be doing with our differential equations, the number is 2 pi. Okay? When it's larger oscillations, this number depends upon the amplitude of the oscillation. But it always depends on the length and gravity in the combination square root L over G. So you get all that for free in units. Okay? Get it for free. G.I. Taylor, wonderful story. You know, especially in this day of an age when we have all this Edward Snowden and WikiLeaks and this concern about classified data. When they did the first tests on the Manhattan Project, they actually showed pictures a little time after in Time magazine. And actually the cameraman let the time of the camera shots, he showed a picture a certain time and then a picture another time, at the front of this mushroom that was coming out. And G.I. Taylor said, oh, from that I can determine the energy of the atomic bomb, which was a highly classified piece of information. So you can bet the Russians, Ildovich and Sergeyev and Sedov and all these people did it immediately too. Just by getting the units right, G.I. Taylor knew that this front, okay, went like essentially the energy per unit mass to the 1/5 power times time to the 2/5 power. Had to go like that. And knowing that, then he could work out the energy. So you get a lot for free by knowing that equations have to balance in terms of numbers and units. Okay? And one of the fun lectures I'm going to give you is I'll teach you how to take advantage of that in certain contexts. Now, I've completely forgotten what I was going to do next. Okay, so we're at the point now we have formulated a few different equations, okay, for various circumstances. Now, this process is something that I want you to do. This is like the equivalent to, remember those problems in algebra when like John and Mary have 10 apples between them, John is 2 more than Mary, how many has John and Mary got? And you write down algebraic equations expressing that fact. Well, you've moved on a little bit. What you're going to be doing is using Newton's law or various laws from chemistry or biology, various rules, empirical. Some of the laws are well tested, some are just empirical, and writing down expressions which actually express what these principles say. But you're going to write them down in mathematics as differential equations, whereas originally the laws are given in terms of statements and prose. For instance, we'll be looking at population growth. And we'll look at the interaction of two populations, of a predator and prey population. And we'll be writing down differential equations for that. The more of these examples you do, the better you get to be at it. Okay? And so it's a very essential ingredient. Now we learn how to solve each of these equations in time. In fact, fairly soon, because they're not terribly complicated. Now, for the last few minutes, I'm going to talk about types of equations, classification. Okay? So we'll get rid of the dead body. Okay. So classification, types. And we're going to do it very simply. The different types of differential equations. So classification. types. And how I'm going to set it out is I'm going to draw a little set of boxes like this. And okay, like this. All right. Now, differential equations tell how certain variables, which we call dependent variables, change with respect to the change of certain other variables we call independent variables. Usually the independent variables are space or time, and the dependent variables are things like temperature or salt concentration and so on. Okay? So if the number, so I'm going to write the number of dependent variables up here, and the number of independent variables down here. And I'm only going to have two categories: 1, 1, or greater than 1, and greater than 1. Okay? So, if you have one dependent variable and one independent variable, we call this an ODE, ordinary differential equation. And an example is dy by dx is minus x over y. So that's called an ODE. In fact, this is the class of equations we're going to study for most of the term. This and this second class here I'm looking at, but mostly this one. If I have more than one dependent variable, but still only one independent variable, think of a situation like, for instance, I have equations for, imagine x is the population of rabbits, okay, and the y is the population of foxes, and a and b and c and d are just given constants. I'll explain why this is a reasonable equation very shortly, I mean in a couple of lectures. You see here I have two dependent variables, x and y, and one independent variable. And this is called a system of ODEs. Okay? If I have more than one independent variable, for instance, supposing I am monitoring the temperature, okay, in a tube as a function of the position in the tube, we'll call it x, and time. Okay? This is called a PDE, partial differential equation, and you will not see any methods for solving PDEs in this course, but in a later course you will. So the temperature, the partial derivative of the function of two independent variables, x and t, the partial derivative with respect to t is some constant times the second partial with respect to x. This is called the heat equation. Very famous equation. It's not only an equation to describe the diffusion of heat, but it'll also describe the diffusion of chemical concentrations. And it also helps you price options. Anybody here going to do finance or economics later on? Yes? Only one. Two. Do you happen to know? Yes, and the third. Does anybody happen to know what the equation for pricing options is called? The Black-Scholes. Black-Scholes. That's the heat equation. Black-Scholes is essentially a form of the heat equation. Okay? Actually, it was Scholes and Merton got the Nobel Prize for the Black-Scholes equation. Poor old Black was dead at the time, and they don't give the Nobel Prize posthumously. So if you ever have a great idea, stay alive. Okay? And then we can have systems of PDEs when you have more than one. For instance, the equations which describe the velocity and the temperature or pressure or density of the atmosphere, that set of equations would be systems of PDEs. The equations for fluid flow, the Navier-Stokes equations, they are systems of PDEs. So these are the types. This guy is the one we're going to study first, okay? And the typical ODE I will write as follows. It'll be a function of, it may depend on the independent variable, on y, this is the dependent variable, its first derivative. It may depend on the second derivative, and all the way up to the nth derivative. Now in the notes, that's given as equation 1,4, which you can find. Now, three types. First of all, the order. The order of this ODE is simply the order of the highest derivative. Which appears. Okay? For instance, what is the order of this differential equation? 1, first. Okay? We also say whether it's linear or nonlinear, and I'll be telling you later why linear equations are very special. Linear and nonlinear means that f depends, or is a linear combination of 1, y, dy by dt, etc., all the way up to dn y by dtn. For instance, this equation here, what's its order? First, because the highest derivative which appears is the first. Is it linear? Yes, because it's just a linear combination of x, 1, and dx by dt. Now, how about this equation? Here, is this linear? No, because the dependent variable appears as 1 over y. Okay? Right? It doesn't come as y. How about this equation? Would this be linear or nonlinear? dy by dt is y squared. What's the order of that equation first? First, is it linear or nonlinear? Nonlinear, right? Third category is autonomous or non-autonomous. And this means that f does not contain the independent variable explicitly. Okay? Explicitly. Okay? How about this guy? Is this autonomous or non-autonomous? It's autonomous because the t, it appears as dx dt, but it doesn't appear anywhere here. How about this guy, if q1 is not q2? Non-autonomous. How about this one? What's the independent variable? It's x. Does it appear? Yes, so it's non-autonomous. Okay, so there are the kind of three categories that we're going to use. That's all we bother with. Now, next day, what we're going to do is I'm going to tell you what do we mean by a solution of a differential equation. And I'm going to tell you how to get the solution in certain simple cases. For instance, this case and this case. All right? Now, I have a clock here which says 12:13. My clocks tend to be highly unreliable. What? 12:08. But look, it's the first day. Recitation, see you Thursday. Oh, collect these. Notes.